Recording in progress.
Okay. Can you hear now?
No, you don't.
Santosh, you have to allow.
Okay. Can you hear?
Yeah, now it's working.
I was basically asking was there any question from yesterday. So if you have any question, I can answer before we start. Okay. Okay. So now I'll just give the summary of. To summary of what are the numbers we know. This we need to know for just your general knowledge. If you are talking about stars, typically the mass can go from 1/100th of mass of sun to up to 100 times mass of sun. So these are very massive stars. So 100 solar mass or 10 to the minus 2 solar mass. Typically, stars also, you see them in groups of stars. We call it as star clusters. Star clusters are typically have masses in the range 10 to the 3 to 10 to the 6 solar mass. Other way of saying is that a typical cluster can have anywhere between 1,000,000 stars to 2,000 stars. Okay? That is the kind of rough estimate. So when you are talking of galaxies, you have galaxies with masses ranging from 10 to the power 6 to 10 to the power 12 solar masses. Such less mass galaxies are known as dwarf galaxies. Dwarf galaxies means basically to say the dwarf, right? It's smaller. And massive galaxies can have up to 10 to the 12. And if you are seeing galaxy clusters, low mass galaxy clusters can be 10 to the 12. That means it's clear that in this particular cluster, there may be one massive galaxy which contributes most of the mass. There may be smaller galaxies. You can think of clusters of galaxies where most of the galaxies have masses of 10 to the 8, and there is one massive galaxy which sits in the center, which can be 10 to the 12. In that way, you can say like biggest mass of the galaxy to be the lowest mass of a cluster, and vice versa. So one can also calculate, for example, the simple number you can calculate, saying that suppose apart from this particular case, in all other cases, what you have is that you have several kind of stars or several kind of objects, individual objects like galaxies. They come together and now they become one bound system. Bound system means they keep rotating with respect to the center of mass, and they preserve the shape in some way. Okay, this is the basic idea. So this is what I told you. This is what is known as real equilibrium. So even real equilibrium can be there based on conservation of angular momentum and energy. So particle in a star cluster, a star can keep moving all over the place, and it will give a shape to take a picture. Okay? And similarly, in the case of galaxies, now you can ask how long it takes for, suppose if I have a collection of galaxies, a collection of points, I put them in a place and let them fall based on the local gravity, how long it will take for it to reach some sort of equilibrium so that they behave in a particular systematic way. So that time is what is known as relaxation time. Relaxation time means a particle coming with some coherent velocity in the beginning, not influenced by all other particles, gravity of all other particles. Now it became a part of a system. If you want to understand, if you take individual electron in a free space, you know that how it is moving, you can quantify. When it is part of a statistical system, you will say that individual electron will collide with each other. Suppose you sit in the electron. After each collision, the direction of motion will change. Its velocity, amplitude of velocity will change. Right? So that means in general, a single electron, if I track the path of the electron for some time, you will find that I can actually have a distribution of its velocity. After each collision, it has some velocity, right? We just allow it to go for some n number of collisions. Then you look at the distribution of individual velocity of a single electron. That will be exactly equal to, I take a snapshot. One time I ask what is the velocity of individual electrons and make a histogram, or I sit on an electron and wait for some time and do a histogram, both of them will be same. If they are same, this is what is the idea of an equilibrium. That means the particles become indistinguishable to the system. They behave the behavior of the system given by the distribution function. How it is possible? It is possible only when you reach a situation that the net energy is conserved, or when one particle loses energy or another particle gains energy. And since the net energy is conserved, the overall distribution will not be altered. Whenever in a location, an electron which is moving with high speed, because of collision, when it becomes an electron with low speed, within the system itself, somewhere else, the electron which was moving at slow speed has now gone and occupied the high speed of this guy. So it has to replace, otherwise the distribution function will not remain same, right? Suppose if I take a high velocity point and make it go to the low velocity, the curve is altered. So you should have similar thing happening other way around, right? So this is the kind of system. So if such things to happen, when we will have mixing, this is like going to college. The first day people will sit separately because you are not talking to each other. But after interacting with people, you will, all the voices of the class will be very coherent because you want to go against the teacher, you want to complain, you will do nicely together. But in the first day of the college, you will not do like that because you are coming with different ideas. The ideas converge only when you interact. So this is exactly what happens among the system of particles also. There should be some time scale over which the mixing of all the quantities like velocity, angular momentum, all should happen among them in such a way that the total thing is conserved. This is known as relaxation time. Ideally, the relaxation time should be related to frequency of occurrence of collisions. How often you can collide, how often you interact. If you interact more often, coming to some kind of global picture will be much easier. So this is very logical way of doing it. So in this particular case, you can now calculate how much time it takes for a particle to interact. That means you can calculate interaction cross-section so that it's exactly like the way you have done in the case of statistical mechanics where you introduce random walks and mean free path of collision, right? Mean free time, and things like that. The mean free time is roughly you can think of like a relaxation time. Some 2 times mean free time, particles will relax. So if you ask what is the kind of relaxation time for a star cluster, if you bring collection of stars together and leave it to undergo gravitational collapse, how long it will take? It will take something like 2 into 10 to the 8 years. A simple way of calculating the interaction will depend upon how often, suppose this is the size of the cluster, how much time it takes for an object in the air to go to the center. This is what is known as free fall time. I just leave it, it will just free fall. So free fall time will tell you how long it takes to cross. And interaction should be few times free fall. It has to move at least few times to interact. So roughly you can visualize why timescales become larger when you have larger potential, because the transit time will be larger.
Can you explain this, please?
That's what. So suppose n number of parts, n is the number density and v is the average velocity and sigma is the cross section. So what is the mean free path? If you want to ask what is the mean free path for collision, that will be 1 over n sigma, correct? Right? N is the number, this one. So what is the mean free time? Time travel taken to travel this distance. So if I know the distance divided by velocity, I will get that. Okay? So if I ask you tau, you are okay? In a gravitating system, what is V? V is the velocity. Suppose if I leave the particle, what is the velocity it will feel? So what will be the velocity if mass is m? Right? The force will be half mv square will be equal to gmm by r square. So you can calculate what will be V. So that V will depend upon the gravity. So what I am saying, so this will be the distance, this will be the time scale, and this will be the distance. Okay. So what I am trying to say, suppose, so it is clear that if the density is very large, the distance will be very small, right? For a given cross section, you will reach equilibrium very quickly. Agree? Your collisions will be more frequent if the density is very large. Okay. On the other hand, I say my time scale now also involved in what is the velocity at which I am moving, right? The other way of saying is, if I move with some velocity, in unit time, what is the volume I will sample for interaction? You can assume as if a particle has an area which corresponds to the interaction cross section, and if you take that interaction cross section, move it across, you will construct a cylinder for unit time. If the cylinder is bigger, there will be more particles which will be covered in that cylinder. That means this test particle which I am throwing, it will be able to sample more particle per unit time if its velocity is higher. Okay, this is what I was trying to tell you. So typically there are few things you have to consider. One is the density, depending upon what is the density of the source, what is the interaction cross section. Interaction cross section here is gravitational. If you come closer, rate will be higher, right? So the point I was trying to say, what is relaxation time? Relaxation time is you can say that a particle will lose its original identity of a velocity. I throw it with some velocity, it will lose its original identity after n number of collisions because it becomes part of the system. So usually the relaxation time will be few times this time, whatever, right? Interaction time. Okay, that is what it is. So what I was trying to tell you is that it is also depend upon free fall time. Free fall time is you take a gravity, you can ask what is the speed at which a galaxy will move in a gravitational potential. That is the free fall velocity, right? Because this galaxy will see as if a centralized mass contributed by all other galaxies sitting in the center, and it will just fall. Okay. So if you take a cluster mass is very high, so all velocity will be higher, but the distances are also large. This is what you have to remember. Potential doesn't tell you the distance. Right? Potential can be very deep in a small distance also. Potential may be stronger, but if it is shallower, the velocity will be still. But velocity will depend upon gradient of potential. Right? Force is gradient of potential. That's right. Okay. Now you are fine. Okay. You understood? I'm just skipping something. Otherwise, you just to do what is the Virial theorem. Virial theorem tells you something that tells you what is the kind of this thing. Then you just calculate the collisional time scale. Collisional time scale you can calculate assuming as if one object is sitting, all other objects are passing by. then you can calculate what is the time scale for collision and things like. So anyway, I will not go into that. Okay, so you get typically the point I want to emphasize here is that if you think of simple collisions, you can see that the star cluster will be okay. You have to wait for 100 billion years, then the star cluster will be created. 100 billion years is not a big deal for a galaxy because it lives for tens of billion years. So it is like 1 part in 100 to get it. But if you look at system of galaxies or galaxy clusters, you begin to wonder how to make them realize. It is not going to be very easy by this simple process of saying that if two guys go close to each other, they will exchange momentum, because collision between two stars or two galaxies are going to be very rare because lot of space between them. So this is a very challenging problem. I just indicated this number to let you know that a simple physics like what we do may not work to calculate what kind of relaxation time. But actually, we know that galaxy groups are there, galaxy clusters are there. There may be some additional physics which we have to incorporate. Just collisional, these things are not sufficient. So this goes by the name violet relaxation. I just mentioned to you. I'm not going into detail because otherwise this whole lecture will go into. Okay, so just to give a number, clearly numbers are very large, time scales are large, but you have to remember. Let me now focus myself differently. What I'm going to do now is that we have. I want to just introduce this idea of what we discussed, that we are measuring distances and all, but there is no instantaneous communication between object and you. See, this is not like instantaneous communication like what happens between us now. Even though we are receiving light from distant sources, when you reach certain distances and beyond, when you receive light today, the source may not be there, but it is gone. Because the light travel time can be much larger than whatever you call the time scale of the object itself. So now I will give you a basic understanding of how to deal with this. Okay, how to deal with this situation where this is going to happen. So that's why I will now switch. I will skip several transparencies because these are covered by somebody else. Because sometime back I would have covered all of them myself. So I'm now going to take you to what is known as extragalactic astronomy. I'll skip few things. So we'll come back to this. So this is what I'm going to concentrate on. Extragalactic astronomy means we are going to worry about things which are outside our galaxy. Other way of saying is that we are actually thinking about large origins of our universe itself. Okay, so I will focus mainly on this topic today. And if you have any other question related to any other astrophysics during the course, and if somebody says that I should have covered this or something, you catch me, I will explain to you. Okay, so I am available during tea breaks or in the evenings. You can catch me. There's no problem. Okay, what is extragalactic astronomy? Observationally, extragalactic astronomy means anything outside Milky Way. Okay. Basically, this also goes by the name observational cosmology. So in this case, what we are going to do is that we are interested in mapping the whole universe itself. So we are not going to, in this particular aspect, when you are dealing with this, you are not going to worry about what these objects are, what they are doing and things like that. We are going to just look at how the objects are distributed, at different times, and we are going to predict the underlying universe based on the distribution of objects. It will be a bit annoying to you what I am saying, but if you visualize like this, suppose if I ask you to map, I want you to give me some idea of what is Pune, but you can about Pune, and I just said like you cannot come and visit by car or anything. You are allowed to go in the aircraft. That's it. And in particular, you are told that you can go only during night. That's it. You cannot do anything else. You have to tell something about this city. So what you will do, you will fly and see the light distribution. Then I think you will be not such a great person or a great individual if you start worrying about why some light is red, why some light is what you will see is that you will see overall distribution of lights, right? And you will see that if you go to Deccan Gilgona, center of the city, there will be huge amount of light. So you can say that I can see there are few city centers where there are large number of people. Actually, you are not counting people there. Are you counting people there? No. You are assuming people are intellectuals. They will not put so much light if nobody is there. Okay, that is the first thing. So you would have said like, okay, now I see that there are several people here, and you can identify the location. That is the first part. That means in this case, what you are doing, you are using the lamp post and lamp as a tracer of underlying location. Correct? So this is basic idea. You will take sources and you will say that you will assign some physical description to how sources are distributed to do that. Okay? So this is the first thing. First thing you will say, there is more crowded region somewhere, there are more houses, or more people around, there are more activities around in some region. There are some region you say less number of this thing. Okay? This is the first part. If you want to go next stage, you will say that like, why should somebody be crowded there? So people will go to a place where they get more money. People will go to the place where they get more, whatever you call, comforts, right? That means there are certain activities which are favorable or which are liked by this tracer which I am using, right? So that means there is an attractor which attracts people towards that. And you can also say when there is no light, there is something which prevents people from going and settling. Okay, so you can clearly see one thing you can say is the distribution of tracers should give an idea of some underlying distribution. In this particular case, in cosmology, you will say underlying space-time. Where there is more mass, you can say that there are more distances. The second question you will ask is that why there is a preference, why certain regions are preferred and why certain regions are not preferred. So this is basic idea. So what basically observational cosmology do is that objects are just tracers of the underlying space-time geometry. You understood, right? I give a reasonably good example. But you have to remember, astrophysical objects born, evolve, and die. So this is interesting. Huh? Suppose if you come up with, we can say this way, right? I am living in a very controlled city where we have been told that certain sections should switch on their light between time T1 and T2. All other people should switch off. Suppose if I declare that way. Then my logic of tracing this thing will go for a toss. Well, what you have done, you are taking a snapshot, but actually people are everywhere because in certain places they switch off the light. So clearly, this is like saying that the light's lifetime is 1 hour, right? Then I will be probing only that population. So clearly, evolution or any modification to a tracer which I am going to do, it will bias me from interpreting what is underlying the distribution. Okay, so that means as far as possible, we have to choose the tracer. You can't look at the supernova and say like I will look at supernova. I will take a snapshot of supernova and decide where matter is distributed because supernova lives for 2 days, right? So this is a problem. So basically, we have to worry about this aspect: astrophysical objects born, evolve, and die. By selection, we pick very peculiar objects at high redshift. This I will explain to you. I have not yet explained what is redshift. But by selection means again, this is like this. Suppose if I make this exercise, that all lights are not uniformly bright. Some certain lights are very bright, certain lights are faint, and you take the photograph. What impression you will get depending upon how the bright lights are distributed rather than how all the lights are distributed. If all the lights and bright lights are not distributed in the same way, you will have a biased thing. So I will explain to you this, okay? There is also physical cosmology. What is physical cosmology? Physical cosmology means you say that, okay, I don't worry about this underlying background, what kind of background universe, what kind of universe in which we are living, whether you have dark matter, dark energy, or whatever, we don't know. I want to understand one object. I take a galaxy. I would like to know how I got the galaxy starting from scratch. So we will ask the question, if I am given a dark matter particle, what happens to gravity of the dark matter particle. When dark matter particle go into some region, what they do to the baryons. And yesterday we saw an example. Dark matter and baryon will behave very differently when they are asked to collide with each other. Okay. So how are you generating energy? How the bulb is? See, this is a different question. Huh? You are given aircraft and camera to do it. Some people will map the city. Some people will start picking bulbs and say, "Hey, this I am receiving so much energy from the bulb. How this bulb is generating energy?" So you can go into that kind of discussion, and we can talk about timescales of equilibrium processes, because we said like relaxation time. A galaxy appears like this and it appears like this every day. It is not changing. So why it is not changing, right? And interaction of surrounding space, you should also worry about if you have one galaxy, what happens to the surrounding regions, whether it is going to attract more gas into it, or it is going to throw away some gas away from it, and what and what not. So light sources probe gas baryons in the sense that light sources, light is the only thing we can detect. We cannot detect anything else. So if you have matter, unfortunately it doesn't emit any light, suppose, then you will never discover. I mean, this is a famous joke, no? I mean, this is what everybody tells whenever they talk about such thing. You would have heard it also. There is a lamp post and somebody is searching around the lamp post. A person passing by is asking, "What are you doing?" He says that I lost my coin and I am looking for it. So this person asks, "Where did you lose your coin?" "I don't know where I lost it." Then this guy says, "Why are you searching here?" "Because I can search only here, because only here I have light. In other places I don't have light, I cannot search." So this is exactly is the problem in this thing also. Like whenever we are doing any exercise, we are looking at place where the light is coming. It doesn't mean that all other places there is nothing, right? Only thing we know is that other places their ability to emit may be less. That is because there is no matter. That is good news for us. Our matter is there, but it doesn't have enough efficiency to convert its energy into some sort of radiation. So these are the things you have to remember. So let's now go back a little bit. I will go through some basic level of cosmology. So there are several things which happen, which is very coincidental. And as I keep saying that there are cosmic coincidences. If things don't move with different speeds, we would not have done various things. So this is first thing. The first thing which happened in late 19th century, early 19th century, is the discovery of expansion of the universe. So what happened was, this is Edwin Hubble. So Hubble went and measured distances of nearby galaxies, and he also calculated the velocity of the galaxies. How do you calculate velocity? You look at the spectral lines from the galaxy, and you see that whether the spectral lines are moving. If it is moving towards you, you will say that it is coming falling. If it is moving away from you, you can say that it is outward. So what Hubble did was he simply plotted distance and velocity, and he found a straight line. Okay, and we can write it down as v equal to h naught into r. Right? This is what my r, and this goes by the name Hubble constant. What he found was, he simply said that objects which are far away appears to be moving away from us. Everything is going away from us. This is what is known as redshift. So all galaxies are redshifted. All galaxies are redshifted. The galaxies far away, redshift faster than. This is the first thing he found out. Further you go, object move faster away from us. I'm sure that you are very happy that every galaxy is afraid of us and running away from us. So this will make us very special, correct? If this is a problem in doing physics, when you find anything which is very specific to us, we have to be quick, right? It cannot happen that we are part of the center of the universe. So whichever direction I look at, things are going away from us. So there is some other explanation has to be found. It is not that galaxies are afraid and moving away from us at high speed. Okay, this is the first experiment, the first thing which was found. The second thing which was found around the same time was the discovery of what is known as cosmic microwave background radiation. So what happened was this HARN antenna was designed, and people were trying to detect various moving objects in the sky using this antenna. And when the antenna was actually installed and when they were trying to make measurement, they were always finding a constant signal. So later on, it was realized that this is not, people thought that some issue with electronics or some issues with this telescope itself, but later on it was realized that it's not noise, it is actually one of the strongest signals in the universe. This is what goes by the name cosmic microwave background. So basically what you do in this case, this is first thing is Hubble, second thing is related to cosmic microwave background, where if you plot lambda versus f lambda and you find Planck curve, and in fact, it is so interesting that this is extremely perfect black body. What is the meaning of perfect black body? This fit just follows Planck curve very accurately. The errors are 1 part in 10 to the 5 at each pixel. If you measure temperature, the error in the temperature is at the 4th of the pixel. So this is extremely good experiment, and it proves that any direction you look at, you have a source which is complete black body, absolute black body. Okay. So these are the two observational things which make people reconstruct what is called a Big Bang. Let's understand this. So let's start with this. It's easy for you, and you are going to answer to me. What is the black body radiation? What is the requirement of black body radiation? An object will emit Planck spectrum. Over that, again, it is in thermodynamic equilibrium. That means radiation and matter, whatever the temperature of the matter, and whatever radiation this matter will emit, will be a perfect equilibrium. So how it is possible? What is the temperature of the matter? The radiation should know. What the spectrum radiation is going to produce, matter should know. This is possible only when matter and radiation are tightly coupled. They exchange energy quickly. Right? Wherever you have equilibrium, means the constituent elements or constituent particles should tightly couple with each other. So what it tells us is that if I look at this direction, if I find radiation field, if it is perfect black body, I know that in this direction there is some place where I have this situation where there is perfect equilibrium between radiation and matter. Now I say that I look at this direction, I also find perfect equilibrium between this and that. Okay, and the temperature is exactly same, right? Whether I look at here, at the level of few decimal places, the temperature is exactly same. So we are clever people, we can build a story. There is some physics which keeps matter and radiation completely coupled here. They are tightly coupled. There is another set of this thing coupled in some other direction. Somehow, they know what should be the temperature. So if they are very far away, it is impossible to do. You understand, right? Because how do I communicate between 2 points? I will communicate by light, and we know that light takes a lot of time to do. By the time light goes from here to here, this guy would have cooled down a little bit, or this guy would have cooled. So clearly, one of the requirements, if you want universe to be at uniform temperature all over the place, you would have done it very easily if the universe was very small. You agree? The universe, you would have done it. But if you want to do it today, it will be impossible. Okay? So now that was one of the things, saying that to produce such a perfect black body, the universe has to be at some stage extremely smooth, and photons and matter are tightly coupled to each other during their interaction. And just to make that large scale coherence is maintained, as much as possible, the universe should be as small as possible when this thing happens. So this we understand. Okay. So this is first part. The second part, we will go back to Hubble expression. So now we will do a little bit of, so this is what we have. V equal to h naught r. And V, how do you calculate V? So you will calculate, so this V I will remove now. it depends on what plus or minus or whatever. In our case, we will put plus v is redshift, minus v. So this is this equation, and this quantity we will call it as z for the time being. Okay. So I can now know what is the laboratory wavelength. I can calculate what is the observed wavelength. So this is my rest wavelength, or if you want, I can do technique lambda rest, lambda observed. So I can now tell you what is the speed at which, the speed means apparent speed for me, speed at which this object is moving away from. Okay, so this is the way we can do. What was happening was these values are this v one is measuring, or this ratio v by c one is measuring, is getting of the order of 0.1, 1, 2, 5, etc. Because we started seeing objects at distances, distances far away from us. But when you measure the shift, the shifted the factor 2 under. Is it possible to have v by c of the order of 2? It violates special theory of relativity. Says that it cannot be more than this. So immediately one realizes, first of all, moving 10 to the power 12 solar mass, the galaxy, with the speed 2000 kilometers per second, where will you get the force? Meaning that itself will be energetically challenging thing to do. So definitely, the interpretation of further objects moving away, the fact that we are finding velocity moving away, we cannot treat it as what? We cannot treat it as a physical velocity. It's not that they are not disliking us and start running away from us. No, it's not like that. It has to be something else. So now, again, without going into, I'm teaching at a popular level only, but when people give cosmology, we'll have exact expression, but you can feel what we are up to with my analogy. So, what is any distance? Any distance d or any distance d can be some absolute value, right? We can think of like this, right? Then absolute value multiplied by a scale. What do I mean by that? Suppose if I ask you to measure what length of this object, there is a physical length, but the length also depends on the what unit I am going to do. Okay? So if you say any observable length, I will write it as a length multiplied by a scale. So let me give an example of this, and then I think with that I will stop, because too much of popularization is not good. So we are going to do this exercise. I have a rubber. The rubber, I have some size, and I can keep stretching. So I have a scale. I put the scale. I hold the scale and rubber in one hand, and I keep the rubber. I hold only the rubber, and I keep moving. I can take the reading in my scale. So at a different time, I will find my distances are different. Right? This is simple measurement. If I know the time difference between them, I can whatever. So now let's change the exercise. I got a rubber. I also got a scale. I hold on to two parts of the rubber and scale. But the scale is not made of steel. The scale is also made of an elastic material. I just hold on to this. I keep stretching. What will happen to the length? Length will not change. Right? So this is the difference. If you ask me, I am doing this. If you ask me, is the length changing? I will say no. But what will you tell me? If you see this exercise, what will you tell me? You will tell me that, oh, no, length is changing. What is the difference? In your case, your mind has fixed a scale, and you see that with respect to that scale, things are changing. In my case, my scale is also changing. I am seeing it, oh no, it's not changing. So clearly, a virtual motion, a motion can be introduced by just changing scales. Okay? So that is the idea. Suppose if you are writing velocity, so if I take this distance, the velocity means what I will do, I will differentiate with respect to time. Usually you will differentiate dr by dt with velocity. You keep this r constant, and you say that dl by d. So you will not use L. In cosmology, you will be introduced a quantity called K. A is called scale factor. So now you will say velocity V will be proportional to dA by dt. Okay. So now let's put it back into this situation. When will you get this? So people now believe you can get it by doing the following. Our universe started from a point and it started expanding, and it is expanding today. It is expanding in such a way that without applying any force, distance between two particles are not altered. That means the relative ratio. Suppose if I have 3 points, if I take ABC, AB by BC, that ratio will not change. Similar. So everything is going. So this is what is known as uniform expansion. If you take two sets of points, ratio should not change. Of course, if one point attracts something, on top of this, these particles can be gravitationally influenced. So when there is no external force, the distances, these points are called co-moving points, in the sense that these points move exactly like the way the scale is moving. So you remember that my rubber example. My rubber and scale are co-moving. With respect to you, they are expanding, but with respect to me, nothing is happening. So that is the point. So now, if you think of what happened to lambda you can think of like when the photon is emitted, the wavelength was small. Imagine the wavelength is embedded in a space-time. It was emitted when the space-time is something like this. After some time, the space-time is expanded. So what will happen to the wavelength? The wavelength will get stretched if it is embedded in the space-time. So if you find Doppler shift of 3 means that the expansion rate is by that factor. So basically, you will see dA by dt, and you will actually have a simple expression. If I find out what is the value, what is the amount by which the wavelength is shifted, that will basically indicate what is the amount by which the universe has expanded. Because you can imagine when the photon was created, it was created with some wavelength. If you are at that point, you will see at that wavelength only, because with respect your space and the source space are same. So you are at the same space time, roughly at the same time, right? So it's like this. If I emit a photon, and if I'm giving a voice in particular frequency, you are receiving at the same frequency, because we are in this wave. Now imagine this photon was created in a nearby galaxy. It is going to take something like 10 to the 8 years to come, or 10 to the 9 years to come, 10 to the 10 years to come, depending upon where the galaxy is. Within this 10 to the 10 years, the universe is not quiet. It has expanded by some factor. What is the amount by which the universe is expanded? Ever since the photon starts from that source and reaches me, that will be seen as a Doppler shift. Okay? So one thing you have to remember, even if you remember any of these things, if somebody says what is Hubble, you will say that if I take distant galaxy, the galaxy appears to move away from us with higher speed compared to the galaxy which is nearby. This is observational. But what is happening? You see that if I take a distant galaxy, the galaxy is far away. The light will take more time to come from that source to me. Within that time, the universe would have expanded from a smaller size to bigger size. The shift I am seeing, what shift Hubble saw, is just a reflection of the amount by which the universe is expanded, and it is nothing to do with object moving from us. This is the first point. So you are agreeing with us? So that is fine. Now, what is the consequence of this? That means what we are seeing, if you go back in time, with respect to that point, our universe is expanded. So now we are also clever people. Suppose you say that this is my timeline, this is my time axis, right? So this was the initial, this is today. I am saying that today I am finding two objects which are separated like this. If I go back in time, they should come closer and closer to each other, correct? So you would think, if I go back in time, at some stage they will not touch each other. This is a problem. this uniform expansion ever since t equal to 0, the consequence of that is that all materials should go back to some singularity. So other way of saying is that one of the predictions is that if you put all matter into denser and denser and denser an environment, what you will have a situation where matter, radiation, you cannot distinguish between them. Because if you go to higher and higher and higher densities, at some stage you will find that if two particles collide with each other and create a photon. This photon cannot go anywhere. It will interact with the neighboring particle, excite them. So this tight coupling between, I'm giving an example, it could be anything. It could be an electron emitting radiation getting absorbed and whatever. That means if you go to very dense situation, first of all, you will not be able to distinguish whether this is a galaxy or whether this is a whether this is a star. You cannot, because all of them put it. This is like no, that when they squash the car into a small thing, when they usually dismantle and compress it, you'll find it will be like a box of metal. We cannot go and say this is my gear and nothing. Everything is okay. So such a situation means one of the consequences that the universe should have started from very low density, very high density, very small compact in very high density, high energy density, matter, radiation, everything, and matter and radiation should interact with each other. Okay, this is the ingredient we want, isn't it? Because if we want to produce uniform black body radiation all over the place, what I need to have a perfect thermodynamic system where matter and radiations are in equilibrium. So it would have happened at some stage. Okay, fine. So now what you are seeing is 3 Kelvin. Okay, radiation is 2.7 Kelvin. This is the radiation you are measuring. So the understanding now is universe was in such a compact region where you are in thermal equilibrium. But if you are expanding, you will reconstruct like this. Take a compact region. If you start expanding, what will happen? You will go to less dense regions as subsequent things. As the density falls, like the way I explained to you about the oscillating star also, when the star becomes very big, the interaction cross-section between photon and particle will go down. That means there will be no interaction. So universe would have been complete thermodynamic equilibrium where radiation matter will be sync with each other, right? And slowly they will decouple, and at some stage the radiation would have decoupled from matter for good. At that time the temperature would have been very high. But since universe is expanding, what will happen? So slowly, so today the temperature become 3 Kelvin. So what one is saying, if you go back in time, so how will you go back in time? These are the two things I will do, and then we'll stop. If you go back in time, you should find more and more temperature for the cosmic microwave background compared to what you are finding 2 Kelvin today. If you go back in time, you should find something. How do you go back in time? So going back in time is that you will pick objects with different redshifts. If you find set of objects where the spectrum is shifted by factor 2, you know that they are coming from region where the 1 plus z is 2 times, right? That means that a of t is this you have expanded by factor same, right? You have double the size compared to what was the thing. Okay. So if I want to go back 10 times smaller universe, I should pick redshift of 11 or something like that. If I take redshift of 100, basically you are picking objects when the universe was roughly 100 times smaller than what it is today. 100 times smaller means distances also is connected. See how you connect between these two, you will learn in cosmology. When they introduce cosmology, there is a relationship between these two. So what one can do, if I ask, instead of asking question, what is the temperature in the previous time, you can ask what is the temperature if I take different redshifts. If I take objects at different redshifts, if the redshift is higher, the temperature should be larger. If the redshift is smaller, the temperature should be smaller. You are with me now? Should I explain again? Okay. So the exercise we want to do is to go and measure the temperature at different locations, at different distances or different times. The way you do, so this is what I explained to you. Okay, the way you do is the following. Basically, what you can do is that how do you measure temperature? How do you measure temperature? Your temperature. See, here we have taken the spectrum and measured the temperature. How do you usually measure the temperature? You have seen two ways, right? One is that when you come from abroad in an airport, they stare at some screen and say, okay, you can. So what do they do there? The thermal imaging. The thermal imaging what? So your body emits some radiation, spectrum. Spectrum is sort of observed. And you know that in that regime, the intensity is proportional to temperature. If your body temperature is high, the intensity will be high to capture, right? Basically, you are using spectral information without touching you, right? Nobody touches you. There is no gadget touches you. But if you go to the doctor, what you will? They will give a thermometer. Thermometer is to setting up another object in thermal equilibrium with you. These are the two ways we can measure temperatures. So if I ask you, I want to measure radiation temperature, some other place, what you have to do? You have to find a thermometer. What is the idea of thermometer? Thermometer means you can pick a, we cannot go on to thermometer. Of course, before going you will die. So the best way is that you have to use some natural things which are available. Natural things which are available are atoms. Atoms, what are atoms? You know that neutrons are there and electrons are in some energy levels. You know when you study laser or something, if you put atom in a radiation bath, these electrons will interact with these photons and they will go to different energy levels depending upon average energy in the radiation. So what you have to do is that you can go to different locations in the universe and take specific set of atoms whose energy levels are such that if they are immersed in the radiation bath, the electron population will simply follow what is the energy density of the radiation field. What is the difference between normal temperature measurement? See, in temperature measurement, what will happen? They will go on, if I give a thermometer to each one of you will not return a uniform temperature. Why? Because each of you have your own thermal equilibrium, your own dynamics of the body and what is out there. So if I just do this exercise, will I be able to conclude anything? Nothing. But I do this exercise in the following way. I make you all sit here in the air conditioned room, make the temperature measurement. I ask you to go and stand in the sun for a few minutes and make a temperature measurement. What will I find? Your temperature will not be very different, otherwise it's a problem. But there will be slight enhancement of all this dispersion between you will be there. It's not that there will be uniform thing, but there will be a uniform increase of temperature of all of you. The other way of saying is, if I do this analogy, right, don't take it literally. So if I just plot temperature distribution, see, this will be around the mean temperature of human beings, you will have a dispersion. So I cannot say much about it. But if I have a controlled experiment where you are in an high school room for some time, some half an hour in a much cooler room, and also half an hour in a hotter room, don't you think you will have something like this? Slight difference will be there. And if you can measure this difference, because this is uniformly affecting all of you, we can attribute to the temperature differences in the room. Correct? This is the basic principle. So you will say that electrons will be influenced by whatever happened locally to you. The temperatures will be whatever happening to, if it collides with without changing temperature, my throat is alright. Okay. So now you understand this philosophy, right? So the electron distribution in atom will be decided locally. But if I pick them from all over the place, there should be some unifying thing that will influence them to go up or down. This is what one uses, and you can measure the temperature like that at different distances. And what one can show or what one finds, these are direct observations. What one finds is that further and further you go, this temperature goes up. The same atoms, all of them will be showing more excitation as we go to the higher redshifts. Okay? And how they are excited can be exactly predicted based on Big Bang, and they match up to 3 decimal places. Okay, this is what I wanted to tell you. So, how are we doing? Okay. So clearly, this is how we can now understand our universe. So I will just give you simple thing. What we understood now is that we say we can understand our universe like this. It is uniform expansion. So this will explain both whatever you call both Hubble's observations as well as cosmic microwave background radiation. Second thing is that we have proved universe was hotter in the. So this set up into this situation where, so what people have done, there are few experiments which are done, which are very interesting. I will just explain to you what is being done. So now you measure this cosmic microwave background radiation, which tells you how the radiation was in thermal equilibrium at some stage, right, with matter. So you can remove these 2 Kelvin contributions. Suppose if you take the spectrum from which direction, you just remove that constant flux, which is corresponding to 2 Kelvin. What will remain is that what is the fluctuation on top of it. This is very small, tiny fluctuations. And also, we are making this measurement sitting in Milky Way or in our this thing. Milky Way is not stationary; it is locally moving. When you are moving, you will also related to Doppler effects. So this is what it is. So this is a map of cosmic microwave background radiation taken in all directions. So you are actually putting in galactic coordinates. This is the galactic plane. If you look at from different directions, we can just plot them here. This is analogous to looking at different directions in the sky. What one finds is that this is 2.7 Kelvin. This is depicted in green kind of light. You remove that flux from everywhere. So constant is removed. So you are looking at the residual. When you look at residual, you find one side is another side is red. Means like one side is slightly hotter compared to another side. That is because this is the direction in which our galaxy is moving. When you move in the cosmic microwave space, radiation coming from this side will appear blue shifted. The radiation coming from behind will appear red shifted. So we know what is the velocity at which we are moving towards Andromeda galaxy. You can remove that component. If you remove that component, this is what you get. So this is the galactic emission. This is our galaxy. Microwave emission from our galaxy. So that is not cosmology. Not coming from everywhere. These are the radiation patches. What you are seeing, blue and green, are the patches which are remaining after I remove all the constant values. These patches have the fluctuations of the order of 1 part in 10 to the minus 5. Okay, if you want to see, there are microkelvin. You think of in temperature, millikelvin and microkelvin level fluctuations are there. Okay, it's a very small fluctuation. So this, if you say, meaning astronomy goes by interpretations of what you see. What we are seeing here is that if I look at the radiation, is radiation coming from an era where the matter and radiations are tightly coupled. If I find the radiation which is coming from that region is completely smooth, intensity is everywhere, it is there, what do you expect? You expect the matter to be smooth also. So let's assume this way. Radiation and matter are completely coupled, but matter is one blob here, another blob here. So what will I see in the radiation? I will see 2 patches, correct? Because the radiation is coupled with them. If I don't see any fluctuation, large fluctuations in the radiation field, what will you conclude? Naively, you will conclude there should be no large fluctuations in the matter field also. So otherwise, this condition that matter and radiation are tightly coupled cannot happen, correct? So first thing about cosmic microwave background, you know that there was a perfect black body existed at some stage, which tells us matter and radiation are tightly coupled. We have a proof that there is an expanding universe. There are 2 proofs. One is the Hubble flow, that is the interpretation, but the direct proof is also there by looking at the temperature, and temperature measurements are consistent all over the place, and it is following Big Bang cosmology. Okay? So this you are completely sure. Now, having understood all these things, when you look at the residual fluctuations, we are finding very little fluctuations. So what does it mean? Matter in the universe at some stage was completely uniform, nearly uniform, at the level of 1 part in 10 to the minus 5. If at all variation, if it is one place 1, another place it is 1.0000 something. So that is the level at which things are uniform. So you can never say something uniform absolutely, right? So that is one point. That means our universe was smooth at some stage, okay? And that is when the radiation decoupled from that. But what is the problem? If it is so uniform, none of us would have created. See, the difference between me and this region, the density contrast is so much. Now, what is the density when your probe is in my body and density outside? So we have already created large inhomogeneities. Like we have created planets, space between planets are not there. But if all of them should have come from that region, which is completely uniform. So what is the challenge one faces in cosmology? This is the problem, right? The problem is, if I look at the galaxy distribution now, today, take SDSS or some survey, find out where the galaxies are. So they remember my light at the city. They will tell you the matter distribution, underlying matter distribution in the universe will be probed by how galaxies are distributed. We said how lights are distributed will tell you underlying population of people, right? So now, if you look at this patch, what do you think? Is it uniformly distributed or you find some patterns? And I find some pattern like a straight line here, I find a straight line here. I find large concentration here. I have no galaxy here. I also see there are no galaxies here. If you look at them in more gory detail, you can clearly see that this is the distance axis, and it's like a slice you are looking at. I take a slice like this and look at locations of galaxies. And galaxies are located either concentrated in this region or galaxy clusters. So I gave you examples of galaxy clusters. We find X-rays, we find like dark matter distribution and whatever. So, but you also have regions which are fixed. But if you go back in time, our universe was extremely smooth. So this is the problem most of us try to address. How do you start from this smooth universe? And only thing given to you is that you can use gravity. Gravity will clamp matter, whichever way you want. Starting from this nearly smooth density fluctuation, how are you going to get this kind of inhomogeneous distribution of matter? Of course, inhomogeneous distribution of matter, you are probing through what you see in light. So you have to also understand, like what I told you, if I look at light, I may look at the underlying dark matter distribution clearly or not. Okay? So these are what are called problems in galaxy formation or problems in structure formation. So we have to do two things. We have to start with smooth universe. And the smooth universe is not going to remain smooth like this because its gravity is going to clamp material. If there is a small deviation from smoothness, that region will grow because gravity attracts. You just make small density enhancement. That part is very easy. But you will also think, if gravity has another problem. If I leave for a long time, all of them would have come to one point. Why it didn't happen? It didn't happen because of the expansion of the universe. There is an expansion of the universe, which prevents you from collapse. This is the good news. That's why expansion is important. But the bad news is, how do you make gravity bring objects together when there is an overall tendency of bringing every object away from each other? So this is a very nice problem. This problem is what we call structure formation. We have some density inhomogeneities. To understand how the density inhomogeneities will evolve in an expanding system. Gravity will try to pull them, expansion pull inwards, expansion will try to push them outwards. So this is a challenging problem to solve, and several of us basically involved in understanding this. We want to understand how dark matter suffers from this. If I put gas, how the gas follow dark matter. Of course, we are not interested in gas, right? We want to convert this gas into stars. And when you have stars, you want to have them planets. When you have planets, you want to have them some atmosphere so that we can produce people like you and me. So the problem is sort of scaled down up to the planets and all, but it has to start from some uniform universe. So this is a challenging problem, and it will be there for coming years because this is not a problem we will solve in one day. But there are some frameworks. in which all of us are trying to work. So I give some idea of, I have not taught you introductory astronomy and astrophysics per se, because we have not, I didn't tell you what is magnitude, what is color, what is parsec, etc. But I hope that I give you a flavor of how astronomy is done. Because if you want to do astronomy, you should know basic physics. Because several of the things I told you, it requires complete understanding of your basic electrodynamics, basic classical mechanics, basic GR, and special relativity. But we will use our common sense and logic to connect various observations, because you are not going to any place and you are not going to perform any experiment like the way you will do in physics. Here it is just observation. So you just observe, and I am sure like you get the logic behind how we reconstructed our whole universe and how we are measuring different quantities which are relevant for our existence, and how interpretations like existence of dark matter and all can be drawn from simple physics. So that was my idea, and I hope that I conveyed this in this lecture. So I will stop here, and if there are any questions you want to ask in whatever I taught, or in general you have, you can ask me. And in case somebody in the online wants to ask me something, you can tell. So no questions today. Yes.
So,
Yeah.
when we discuss about cosmic background radiation, you said that it exactly obeys the background radiation curve.
Black body.
Black body radiation curve. Doesn't mean that we have perfect black body, but we can't locate it.
Yeah. We have located. That is the universe which was tightly interacting, and as universe is expanding, at some stage this radiation has now left the matter. Since the radiation is no more interacting with anything, it remains black body. So once you create a black body and leave it without any additional injection or removal of energy, it will remain like a black body. So this black body is nothing but our universe when the universe was 1,000 times smaller than what we are today. So this can be precisely fixed. This epoch can be precisely fixed. I am not going into the detail, but we know exactly when it happened.
Gravity is trying to keep things together. So, what is the reason for expansion? Which force is like causing the tendency to go away from?
Yeah. So what causes the expansion? You will learn, because you can write down space-time, the dynamics of the space-time in terms of all the available energy densities of the universe. So you will learn that. So expansion, now you can have questions like where it is expanding into. See, you have to think in 4 dimensions, right? So I will leave it. You just go through proper. If you are curious, you start learning some basic cosmology, and there is a nice book by Jack Naliker. There is a small book. It will be available in our library. I can physical cosmology, small, very small book by Jack Naliker, and where nicely all these things are put in place. I will recommend you going through that. And what is the rate at which it expands? Everything can be written in terms of energy density. And you can even find out under certain conditions, the expansion can be reversed also. It is not necessary that the universe should be always expanding. So you can actually, if you write down what is known as metric, which governs the dynamics of the space-time, and the constituents of the space-time will dictate the dynamics of the space-time. You can actually understand the whole thing. There is no problem. I don't want to oversimplify this one. If I start explaining you something, I will make mistake. So better we stick.
When you talked about the relaxation time of the different objects, it was in the scale of 2 to 10 to the power 8 years and so on. Isn't that almost like very close to the age of?
That's what the simple relaxation by collisions is difficult.
So it's still not reached the relaxation
No,
time?
no, no. Our understanding of relaxation has to change because it is relaxed. Now you see that clusters are seen, and I explained to you that they emit uniform X-ray radiation of constant temperature. That means there is real equilibrium. Real equilibrium means they have relaxed. If it is 10 to the 14 years, it is more than age of the universe. It cannot happen. So the way I was trying to explain to you, if I take two particles, they will collide with each other and exchange momentum. After the n collisions, the particle will not have independent initial values. They will follow what is governed by the system's distribution function. But that in gas, it happens by collisions, simple collisions. But here we have to introduce something else to decrease the time scale. This is what I said. There is a thing called violent relaxation. One has to do that. In some way, you have to worry about. I will explain to you later. If there are other questions. No, Hubble constant cannot be. It's not a constant. It is variable because it just tells you about the. That's meaning like a double derivative of the scale factor itself, right? So again, I will say that is depending whether the universe will accelerate at what speed or whether it will decelerate. It depends on the constituents. How if I see simple thing you want to see, if I put matter, normal matter, and expand, the density will fall as Q, right? If R is a scale, density will fall as particle density will fall as Q. If I put radiation if I change, the energy density will fall as to the power 4 because even wavelength is changed. In addition to volume change, wavelength changes, that changes the energy density. So that is why if I put a relativistic particle, the way it will respond to the energy density will change to the expansion. Or if I put dark energy or dark matter, these are all very different. So what one does is that you put all the constituents in a region, and the expansion you see that how the constituents change their characteristics. Depending on that, the expansion rate will be decided. So every time the change in energy density will decide what happens. Different energy density will decide. That's why I told her also, you have to write down expression for the evolution of the space-time and how it is governed by it. This is all there in standard textbooks. So I suggested this book, or there is a book by T. Padmanabhan again. So if you look at it, they clearly explain expanding universe, how different energy densities, for example, how radiation will change as a function of time, how relativistic matter will change. You put neutrino, what happens in neutrinos? So all constitute to the energy density. So it depends. So it is not necessary that rapid expansion or acceleration is the final. Anything else?
There's some questions on Zoom. I'll unmute one of the participants who's raising their hand. Subrata, go ahead. Or in the meantime, we can take the questions from chat.
No, I'm not going to take questions on velocity. If somebody asking what is velocity and all, I have explained. This is not velocity. You guys have any confusion about Hubble expansion? It's not velocity, right? There was a question related to that. I think I will not go into this because I explained enough. My thought is also, I will conserve this thing. Okay, if you have any other question, you can send me email. You know my address, right? We'll stop here.